Okay, in this video we'll continue talking about chapter 6. Here we will be talking about Lewis structures. So what is Lewis structure and what are Lewis theory? Lewis bonding theory basically emphasizes the importance of valence electron. Like we have discussed before, whenever compounds are formed, what the way these compounds are usually formed is by either sharing electrons in covalent compounds or by transfer of electrons. For instance, that transfer of electron usually happens in ionic compounds. So what the electrons that are basically transferred or shared between atoms, those electrons are usually valence electrons. So Lewis bonding theory basically tells us the importance of valence electrons. So whenever we are drawing a Lewis structure, we basically use dots to represent the valence electrons that are either present on the atom or they are being shared by the atom. So whenever you see a Lewis structure and you see any dots on that structure, each of those dot is representing one valence electrons. So the idea of this theory is that we can basically prepare the structure of the atom and we can predict what valence electrons are being shared, what is the arrangement of electrons, and what is the shape of that particular molecule. And for determining all of that information, Lewis bonding theory is very helpful. So here you can see some of the examples of Lewis dot structures of some of the elements. These Lewis dot structures are also referred to as the electron dot symbols. Why? Because again, electrons usually are represented as dots. How do we write the Lewis symbol for if we are just working with an atom? For instance, let's say I'm working with lithium. Where is lithium located? If you look at periodic table, lithium is found in the group number 1. And the number of valence electrons that is present in any group number 1 is given by 1 electron. So remember, valence electron, again, the number of valence electron for any atom is equal to the group number that it belongs to in the periodic table. So lithium belongs to 1, meaning it has 1 valence electron. So if the question is asking you, can you draw the Lewis structure of lithium? You basically write the symbol. The symbol represents the nucleus and all the inner electrons of that atom, and the valence electron is represented by a single dot like this. So if you see one dot, that means this has one valence electron. If I'm writing the structure of beryllium, beryllium essentially belongs to group number 2, so it means it has 2 valence electrons. So you write the symbol and then you draw 2 valence electrons around this. Okay, 1, 2. Now very important thing here is that whenever you're writing the structure of drawing the Lewis structure of an atom, you should always distribute electrons separately, okay, around the 4 sides. So for instance, let's say if I'm drawing the structure of carbon, carbon belongs to group number 4, so it has 4 valence electrons. So how would I draw the Lewis structure? I have to draw 4 dots around it. How would I draw these 4 dots? I would distribute 1 dot on each side of this atom. I will not be pairing any of these dots as of now. Okay, you always distribute these dots around all these sides, and when you have more electrons left, you can start pairing those electrons up. What do I mean by that? Let's pick the next example, which is nitrogen. Nitrogen belongs to group number 5, which means it has 5 valence electrons. So I need to distribute 5 electrons around this. I start by distributing 1 electron to each side. 1, 2, 3, 4. Now since I have 1 more electron left, I will draw it as a pair of electron. Okay, so this is the valence or Lewis dot structure for nitrogen. How about oxygen? Oxygen carries a total of 6 valence electrons. It belongs to group number 6. So we need to distribute 6 electrons around it. How would we do that? Again, do not, even if you can see that it has 6, do not start by pairing the electrons up. Always give 1 electron on one side. 1, 2, 3, 4, and now we can start pairing. So it would be 5 and 6. So basically it will consist of 2 electron as pair and 2 lone electrons. Okay, these are lone electrons. Next, let's pick example of fluorine. Fluorine is belonging to group number 7, so it has 7 valence electrons. So let's start distributing around it. 1, 2, 3, 4, and now I start pairing 5, 6, and 7. Lastly, let's pick the example of neon. Neon belongs to group number 8, so it has 8 valence electrons. So we'll start pairing 1, 2, 3, 4, 5, 6, 7, 8. So that is the structure of Lewis structure of neon. Now what is important when you're drawing the Lewis structure? Remember, every element or every atom is trying to achieve the electronic state of inert gases or noble gases. For instance, what does that mean? They are trying to attain 8 electrons in their valence shell. So something like this. So neon, it belongs to inert gases or noble gases. See, neon has 8 electrons. Except a few examples, most of them are trying to attain 8 electrons in their outermost shell. Okay. We can also draw the Lewis structure for a molecule. So right now what we did in the previous example, we drew the Lewis structure of just the atoms. Now if we are drawing a molecule, we can draw the valence electron for a Lewis structure for the valence electrons of a molecule as well. Here basically the idea is that we are trying to arrange the electrons so that each of the atom has octet completed. So we are trying to see that each atom at least has 8 electrons in its around itself. Okay, there are again some exceptions to this. We'll talk about those in a little bit. Now whenever we draw the Lewis structure, it would look something like this. Let's actually draw a Lewis structure first. So let's see what are the rules that whenever we draw Lewis structure. So here are some of the rules. The first thing you do is you write the formula of the compound would be given to you. So you attach the atoms together in a skeletal structure. What do I mean by that? For instance, let's say I'm drawing the structure of PCl3. Okay, we'll pick an example. Let's say I'm drawing the structure of PCl3. The first rule is attach the atoms together in a skeletal structure. How would you do that? Most metallic element is generally in the center, or sometimes the central atom tends to be the least one in the formula. So if I'm looking at this particular compound, it consists of phosphorus and chlorine atoms. Which of these two is more metallic? We have learnt about metallic character in the periodic trends in one of the previous videos. So based on that rule, you would know that everything that lies, the metallic character basically reduces as we go from left to right in the periodic table. So chlorine is less metallic, phosphorus is more metallic, which means phosphorus will be in the center. The other rule also gives you another hint that the central atom usually tends to be the least one in the formula. So here we have only one atom of phosphorus, 3 atoms of chlorine, meaning the least number of atoms are present for phosphorus. So phosphorus will be in the middle. Then the rule also tells you halogens and hydrogens are generally terminal. Halogen means everything that belongs to group number 7. Chlorine belongs to group number 7. Also, hydrogens are generally terminal. Terminal means they will be, whatever comes in the middle will come in the middle, in the center. Rest, everything will be around it. So I'll distribute chlorine. We have 3 of those, so I'll distribute chlorine on 3 sides of phosphorus atom. Another rule is, which you can remember, it doesn't apply to this example, but in case of oxyacids, the acid hydrogens are attached to an oxygen. Oxyacid basically means something like H2SO4. So oxyacid means it consists of hydrogen. They will always start with hydrogen, the formula, followed by one non-metal and another oxygen non-metal. So it will always consist of oxygen and hydrogen and some other non-metal. If it is like this, you put this atom, the loner atom, in the middle. That would be your central atom. Oxygens would be around it and hydrogens would be terminal. So hydrogens will always be attached to the oxygens around it. Okay, that is what the first rule tells us. Then we come to the second rule. The second rule says calculate the total number of valence electrons available for bonding. Total number of valence electron means use the group number of periodic table to find the number of valence electrons for each atom. Then you add those up, add or sum it up. If you have a cation meaning if it is positively charged, you subtract 1 electron for each positive charge. If you have anion, you add 1 electron for each negative charge. In this case, if we are working with PCl3, the molecule is neutral. So it's not neither a cation nor an anion, so we don't have to worry about it. But what is the total number of valence electrons? If we look at periodic table, phosphorus, I'll write it right here, valence electrons. Phosphorus, each phosphorus atom, it belongs to group number 5. So the total number of valence electron here is phosphorus. For phosphorus is 5. How many valence electrons does phosphorus have? 5. How many atoms of phosphorus do we have here? Only 1. So it would be total number of valence electron coming from phosphorus is 5. How about chlorine? Each chlorine has 7 valence electron. It belongs to group number 7. How many atoms of chlorine do we have? 3, which means I have 3 times 7 valence electrons coming from chlorine. So in total, this would give you 5 plus 21, which is 26 electrons. It's neutral, so we neither add or nor remove any electrons. So total number of electrons here is 26. That is second rule. Going to the third rule, it tells us attach the atoms with single bonds, which is represented by a single line. So we'll draw one single line between each of these atoms, and this single line essentially represents 2 electrons. In a single bond, atoms share one pair of electrons. So each bond that we drew right here, each line that we drew represents one single bond. Okay, and it represents use of 2 electrons in between. Now subtract the electrons that are used already from the total. So total number of electrons were 26. How many electrons have we already added in this structure? Each line represents 2 electrons. So I've added 2, 2, 2. A total of 2, 2, 4, 5, 6 electrons I've already added. So what would be the electrons that is left? Out of 26, I've added 6, which means I still have 20 more electrons left that can be added in this Lewis structure. Next, we move on to add the remaining electrons in pairs to complete the octet of all the atoms. Remember, hydrogen only wants a total of 2 electrons. So now we will start adding these 20 electrons to each of these atoms. How do you start adding these electrons? The first rule is they should be added in pairs. You don't put them separately. You basically keep these electrons in pairs. Second rule is if you have any hydrogen atom in your structure, it will only consist of 2 electrons. And that means if a hydrogen has already made one single bond, you do not add any more electrons to that atom. Next, don't forget to keep subtracting from the total. Complete the octet on the terminal atoms first. So this is the next rule that's important. We first add 8 electrons to terminal atom and then we work towards the central atom. Okay. So terminal means we first start from a corner atoms. So how many electrons in total do we have? We have 20 left. So I'll start giving 20 electrons to this molecule. So I'll start from here. 1, 2, 3, 4, 5, 6. Then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I still have 2 more electrons left. So I'll give those electrons now to the central atom, which is 19 and 20. Okay. So now why did I put these 2 electrons on each side? Remember, we are trying to complete the octet, so you cannot add more than total of 8 electrons on each atom. So how about this chlorine? Let's see how many electrons does this chlorine consist of now. This chlorine has 1 and 2 electrons coming from this single bond, right? So it has 1, 2. Each of these bonds you should count it as 2 electrons. If you can't remember that, you can always draw 2 electrons right here. Now you can start counting for chlorine. So chlorine has how many electrons? This total number of electrons: 1, 2, 3, 4, 5, 6, 7, 8. So if it has 8 electrons, that means this chlorine atom is happy, it is satisfied, the octet rule is completed. Okay. How about this chlorine? This has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this is also 8 electrons, so this atom is also happy. Let's compare this chlorine. This has 1, 2, 3, 4, 5, 6, 7, 8 electrons as well. So this is also happy, right? How about phosphorus? Now phosphorus has all these electrons. Each bond, remember, these single bonds are shared within them, shared between 2 atoms. So how many phosphorus has? 1, 2, 3, 4, 5, 6, 7, 8. So this phosphorus also has 8 electrons, so phosphorus is also happy, which means each atom here has 8 electron. Octet is complete for each atom, so this Lewis structure is good. Unless octet is completed for each of the atoms, you cannot end your Lewis structure. That is not your complete Lewis structure. Okay. This is the Lewis structure for PCl3. Remember, hydrogen always only wants 2 electrons. The last rule is, if there are not enough electrons left to complete the octet of the central atom, bring pair of electron from an attached atom in to share with the central atom until it has an octet. This rule doesn't apply to PCl3 right now because everybody is happy here, but we'll practice a couple more examples where you will be ending up using rule number 5. So what is rule? It tells us that if there are not enough electrons to complete the octet of central atom, so in this case, if the central atom right in the middle, you can't complete at the end, you drew your structure, you're trying to confirm if everybody is happy. In case the central atom is not happy, its octet is not complete, you will bring a pair of electron from the attached atom in to share with the central atom until its octet rule is completed. Okay. And lastly, it says try to follow the common bonding patterns. What does that mean? The common bonding pattern essentially means, I'll come to that in a little bit, but let me first draw the final structure, because this is not the answer that you're going to give in the exam. The answer would be P. Each of these middle electrons, you basically, that shared electron that you see in the bond, you don't draw those. You instead draw a single line. Each line represents a single bond followed by these atoms, and then draw all these electrons. So phosphorus has 2, chlorine has 2, 2, 4, 5, 6. So this chlorine also has 6 electrons around it, 6 around it, and then a bond. Now I want to give you another definition of a couple things here. So these electrons that you see in pairs around, okay, first of all, this would be a final answer, okay, without any of this green that I just drew. This would be a final answer. Now let me give you some definitions here. All these electrons that you see around the atoms, these electrons are present in pairs. These electrons are called as lone pairs. Okay. The electrons that are present in these bonds that you see, that we usually don't draw, these electrons that we see in these bonds, right here, let me draw them with a different color. These electrons are referred to as bonding electrons. Okay, these are bonding, bonding electrons. Bonding electrons are the electrons that are shared in a covalent bond. Okay. all the other electrons that are around this, which is essentially the lone pairs that are present, they are also called as non-bonding electrons. So sometimes the question could be as simple as this. So in the structure of PCl3, how many non-bonding electrons or how many lone pairs are present, how many non-bonding electrons are present on phosphorus? So if you draw the structure, your phosphorus has 2 non-bonding electrons, so the answer to non-bonding electrons would be 2 on phosphorus. How many lone pair does phosphorus have? Lone pair means we are talking about how many pairs. So phosphorus only has 1 lone pair, so your answer would be 1. How many lone pairs does each chlorine have? Each chlorine atom has 1, 2, 3, a total of 3 lone pairs. How many non-bonding electrons does chlorine have? 1, 2, 3, 4, 5, 6. 6 non-bonding electrons. How many bonding electrons are present in the molecular structure of PCl3? So it consists of 1, 2, 3, 4, 5, 6. So it consists of 6 bonding electrons in case of a molecule of PCl3. So you should know how to differentiate between the electrons. Okay. Now we'll move on to slide and we'll try out some more examples. Before we actually do the example, remember in the last rule we saw that there are some patterns that usually exist. So the rules told you try to follow the bonding pattern. The bonding pattern essentially is this right here, that is explained to you in the table. This is the typical bonding pattern for some non-metals, which means typically an atom of hydrogen will only form one bond. An atom of boron usually forms 3 bonds. An atom of carbon or silicon usually form 4 bonds. So 4 bond means here we are talking about total number of single lines that you're going to draw around the atom. Elements like nitrogen and phosphorus usually form 3 bonds each. Element like oxygen usually form 2 bonds each. Element like fluorine, chlorine, bromine, iodine usually form 1 bond each. Now the question would be, do I have to memorize this? The answer is yes. And the second question is, how can I memorize everything? Okay, so the easy way to memorize this, again you look at the group number. Okay, this is based on how many other valence electron does it want. So if you look at hydrogen atom, it belongs to group number 1. So it has 1 valence electron. If it has only 1 valence electron, it can only form 1 bond, because to form one single bond you need to share an electron. Each atom has to donate 1 electron. It has to share 1 electron. So hydrogen can only share 1 electron, which means it can only form 1 bond. Boron belongs to group number 3, meaning it has 3 lone pairs. No, sorry, not lone pairs. 3 electrons in its valence shell, or 3 valence electrons. So each of these electrons can be used to form one single bond. So basically it can form 3 single bonds. How about carbon? Carbon belongs to group number 4, so it has 4 electrons in the outermost valence shell, which means it can form 4 bonds with any other element. Nitrogen belongs to group number 5, so it has 5 valence electrons, right? So if I draw 5, 1, 2, 3, 4, 5, it has 5 valence electrons. How many does it want? It wants a total of 8 valence electrons, which means how many extra electrons does it need? It needs 8 minus 5, which is 3. That is why nitrogen can make, usually it will make 3 bonds. Same thing with phosphorus. This nitrogen and phosphorus are usually an exception. They usually like to make 3 bonds, but sometimes they can make even more bonds than 3. Okay. The next element we see is oxygen and sulfur. They belong to group number 6, meaning how many valence electron do they have? They have, oxygen would have 6. So 1, 2, 3, 4, 5, 6. In order to get 8 electrons, how many more does it need? It needs 8 minus 6. So 2 more electrons, which means it can form two more bonds. Like this can form one bond, this electron can be used to form another bond. So it can form maximum of two bonds each. Fluorine belongs to group number 7. So fluorine has 1, 2, 3, 4, 5, 6, 7. It has this one lone electron. So in order to make this into a pair, it can form one more bond. Or you can simply do 8 minus 7, which will give you 1. So it needs one more electron. How will it get one more electron? To get every single electron, it has to form one bond. So fluorine, chlorine, bromine, iodine, each of these can need one more bond, can form only one more bond. The exception here is, remember, hydrogen. When we talk about completing the octet, the hydrogen is an exception. Hydrogen is not looking to have 8 electrons. It is only happy with 2 electrons in its outermost orbit. Same thing with boron. Both hydrogen and boron do not form octet. Hydrogen atoms share 1 electron pair. It is happy with 2 electrons. Boron atom usually share 3 electron pairs for a set of 6 electrons. So boron is happy with 6 electrons. As long as boron has 6 electrons in its outermost orbit, it is happy. As long as hydrogen has 2 electrons, it is happy. The rest, everybody else wants 8 electrons in its outermost orbit. Okay, so let's now remember all these rules and practice some questions. Okay, for instance, let's say if we were to draw the Lewis structure for a molecule of methane. Methane is CH4. Again, I do not expect you to memorize this name methane as of now. I'll give you the structure CH4 and I'll ask you, can you draw the Lewis structure for this? So how would we draw the Lewis structure? Again, we first have to form the skeletal structure. So we'll follow the rules. Okay, first from the skeletal structure. How would be the skeletal structure formed? You need the atom which is present in lesser amount. Least amount would be center. So carbon would be center. Hydrogen will be all around it. Hydrogen, 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 hydrogen. Okay. Now we need to identify how many valence electron does it have. Actually, let me draw the structure right here at the very bottom. Okay. So carbon, hydrogen, 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 and hydrogen around it. Now we will be basically we have to figure out what is the total number of valence electron. So carbon, CH4, carbon has how many valence electron? 4. Each hydrogen has 1 valence electron. We have 4 hydrogen atoms right here, which means it would be 4 times 1. So total would be 4 plus 4, meaning 8 electrons. So we need to distribute 8 electrons around this. So now the next rule is we basically draw a single line or a single bond between each of these atoms, and each single bond represents 2 electrons. So we have already added how many? 1, 2, 3, 4, 5, 6, 7, 8 electrons. So we have already given 8 electrons. How many more electrons are left? Out of the total is 8. We already gave it 8. So we have no more electrons left, meaning this is the final structure of our CH4 molecule. Now let's confirm though that is each molecule happy? Always confirm. So in case of here, the hydrogen has how many electrons? It has 2 electrons coming from this bond, which means hydrogen is happy. Remember, hydrogen only wants 2 electrons. How about this hydrogen? Same thing. This has 2 electrons coming from this bond, so this hydrogen is also happy. How about this? This has 2 electrons coming from here, so this hydrogen is also happy and satisfied. This hydrogen also has 1 bond, so it has 2 electrons, so this is also happy. How about the middle atom, which is carbon? So all these bonds, carbon is making 4 bonds, meaning 2 electrons coming from here, 2 from here, 4, 2 from here, meaning 5, 6, 2 from here, 8 electrons. So carbon is also happy. So each element is happy. So your final answer here would be carbon, single, 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 single bond with hydrogen. So that would be the final Lewis structure for CH4. Now let's try another example, which is HNO3. How can we draw the structure of HNO3? So for drawing the Lewis structure of HNO3, we would first recognize that this is an oxyacid. How do I know this is an oxyacid? Like I said previously, an oxy acid would always start with hydrogen. It would always consist of oxygen, hydrogen, and followed and another molecule or another non-metal. So this consists of hydrogen, oxygen, and a non-metal, and it is starting with hydrogen, meaning this is oxy acid. Now, how do you make the skeletal structure for an oxy acid? You always put the central atom, which is the central atom is the third element other than oxygen and hydrogen. Whichever element is other than oxygen, hydrogen, that comes in the middle. So nitrogen will be written right here. The next rule in the oxy acid is that you always put all the oxygen around or next to the central atom. So oxygen will be put right here, 1, 2, 3. Next we'll put the hydrogen, and the hydrogen is always terminal and it is always attached to the oxygen. So any of these oxygens you can pick and we'll put hydrogen right here. So now this is the skeletal structure. The next is we figure out what are the valence electron. Hydrogen, I have only one of those. Each hydrogen has one valence electron. Then there is nitrogen. There's only one nitrogen. Each nitrogen has 5 valence electrons. Then we have oxygen. We have 3 of those. Each oxygen has 6 valence electrons. So in total, this would give you total of 24 electrons. So we need to distribute 24 electrons here. Let's start with the single bonds first. So I'll connect each of these with single bonds. 1, 2, 3, 4. Now remember, each of these single bond is 2 electrons. So we will be counting those 2 electrons in and subtracting it from 24. So how many electrons have we added already? 1, 2, 3, 4, 5, 6, 7, 8. I've already added 8 electrons. So what is left is 24 minus 8, which would give you 16 electrons. So I need to now distribute 16 electrons around this. So where do you start? Again, we can start with the terminal atoms. Hydrogen. Do I add more electrons to hydrogen? Answer is no. Why? Because hydrogen is happy with 2 electrons. It already has 1 bond. As long as hydrogen has 1 bond created, you cannot add more electrons to hydrogen. So what is the next one? We'll start adding electrons to oxygen. So this oxygen already has 1, 2, 3, 4, 5, 6, 7, 8, right? So basically all 4 sides should be with electrons. So let's start counting again. We need 16. We have added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've already added 16 electrons and I'm done with all the electrons. I cannot add any more electrons. So this is done. Now let's see if each of my atoms here is happy and satisfied. How about hydrogen? Hydrogen has 2 electrons. So this is happy. How about oxygen? Oxygen is this in all. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So oxygen is happy. How about this oxygen? It has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this oxygen is happy. Octet means 8. How about this oxygen? This has 2 electrons right here. 3, 4, 5, 6, 7, 8. This oxygen is also happy. How about nitrogen? Oh, nitrogen only has these bonds. So it has 1, 2, 3, 4, 5, 6. Which means nitrogen here is not happy. It only has 6 electrons. It needs 2 more. So now we will have to go to the rule number 5, which was whenever the central atom, octet for the central atom is not completed, you can take a pair of electrons from the atom that is attached next to it and we can share those electrons to the central atom. So this oxygen has these lone pair, which means it has these extra electrons which it is going to share with nitrogen. So this oxygen will share the electron, and instead of having a single bond, now we will have double bond between this nitrogen and this oxygen. So the structure now would look like this. Nitrogen in the middle, this would be OH. Oxygen has 2 electrons. This oxygen would be right here, 1, 2, 3, 4, 5, 6, and this oxygen would be 1, 2, 3, 4, and a double bond. So if you add a double bond right here, this oxygen still has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So nitrogen is also happy. So in this structure, every atom has an octet completed along with a hydrogen which only wants 2 electrons. So this would be the final Lewis structure for HNO3, right? So if sometimes the central atom is not happy, you basically can take electron from the outside atom and give it to nitrogen. Now what is the difference here? I took the electrons from this oxygen. Why not this oxygen? Okay, first question is that. Second question is, I took electron from this oxygen. Why not this? You can take electron from this oxygen or this is oxygen. It would still be the same structure, right? That would mean this oxygen has a double bond with nitrogen, or you could draw this oxygen with a double bond, this oxygen with a single bond. It really doesn't matter. They are the same atoms. But if you take the electrons from the oxygen, which is OH, and give it to nitrogen, then that would make a difference. And the difference is that your structure would be wrong. Why is that? Because remember, the typical pattern of making bonds for different atoms, we saw that the typical bonding pattern for oxygen is that it can only maximum form 2 bonds. This oxygen right now has already formed 2 bonds, which means you cannot take these electrons and give it to nitrogen, because in that case you will have to make 3 bonds for oxygen. Oxygen never has 3 bonds, oxygen only carries 2 bonds. So since it already has 2 bonds, you cannot take electrons from here and give it to nitrogen. The electrons has to come from the other oxygen, right? Another thing that you would say now, that the typical bonding pattern also tells us that nitrogen can only maximum have 3 bonds, but I told you nitrogen is an exception. Nitrogen and phosphorus, they can sometimes have more than 3 electrons. So here you can see nitrogen has 1, 2, 3, 4 bonds. So this nitrogen is an exception. It can usually form 3 bonds, but sometimes the number of bonds can be a little bit more. It can be 4, it can be 5. So that is HNO3. Okay, so here are a couple more examples. PCl3 is something that we already did. So now let's work with C2Cl4. So this, when we are working with this example, I would like to give you a couple more suggestions or rules that you can use. So for instance, whenever you see a compound with carbon present in it, if the number of carbon atoms is more than 1, these carbon atoms are usually connected to each other by a bond. So what do I mean by that? Whenever we are drawing a structure of something with carbon like this has 2 carbon atoms, so our central atom here is going to be 1 carbon, second carbon, and the rest, everything else that you see, will be distributed. Try to distribute it evenly to both of the carbons, meaning it has 4 chlorine atoms, so I will draw 2 chlorine atoms next to one of the carbons, and then 2 chlorine atoms will be bonded to the other carbon atom, and now we'll draw single bonds between them. So the idea is that you first draw 2 carbon atoms, they would be connected to each other by 1 bond, and then distribute whatever's left around it evenly. Okay. Alright, so if we continue with this, now we need to figure out, this is a skeletal structure, we need the valence electron. Each carbon carries 4 electrons. We have 2 carbons, so that means I have total 2 times 4 electrons coming from carbon. We have 4 chlorine. Each of the chlorine is 7 electrons, so we have 4 times 7. So total number of electrons here would be 8 plus 28. That would give you 36 electrons in total. So we need to distribute 36 electrons around this atom or around this molecule now. Okay, and how can we start distributing these electrons? We'll again start with the terminal. First, let's count how many have we already distributed. We have given 2, 2, 4, 5, 6, 7, 8, 9, 10. Then we can start from here. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So now we have 36 electrons distributed around this particular molecule. So now let's see if each of these atoms is happy with the electron distribution. So this chlorine right here has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this is happy. How about this? It has 2 electrons right here. 3, 4, 5, 6, 7, 8. This is also happy. This chlorine is 2, 3, 4, 5, 6, 7, 8. This chlorine is happy. This chlorine atom has 2 electrons, 3, 4, 5, 6, 7, 8. So this chlorine is also happy. This carbon right here has 1, 2, 3, 4, 5, 6, 7, 8. So this is also happy. This chlorine has 1, 2, 3, 4, 5, 6 electrons. So this carbon, sorry, did I say chlorine? Last time carbon. This carbon is not happy, which means it needs another lone pair of electron. If it isn't happy, you basically take the electron from the attached atom and give it to this central atom. Now I could take these electrons from chlorine and give it to this carbon, but that would be wrong. Why? Because remember, chlorine can typically only form one bond. If I take these 2 electrons and share it with carbon, this would mean that it would form a double bond right here. Chlorine cannot form 2 bonds, it can only form 1 bond. So I cannot take these electrons from chlorine and give it to, share it with carbon. The carbon, on the other hand, this carbon, I can take these extra lone pair of electron and share. If I do that, what would happen? These electrons will go right here. There would be a double bond now. So now this carbon can have 1, 2, 3, 4 bonds. This would be happy. This carbon can have 1, 2, 3, 4 bonds. Remember, each carbon typically makes 4 bonds. So this structure looks pretty happy. Everyone would be happy and satisfied. So your final structure now would look like this. Carbon, carbon, there would be a double bond in between, single bond Cl, single bond Cl, single bond Cl, single bond Cl. And now you distribute these electrons around chlorine. Each chlorine has this line that you see sometimes show up. That is just like a technical thing that happens. You definitely don't need to draw this line. This is just happens when I'm using the pen. So this would be your final structure, except this line, of course. This would be your final Lewis structure for C2Cl4. Okay, here every atom in this molecule is satisfied and the octet rule is completed. Okay, we can try a couple more questions. Here are some more examples that we can practice. For instance, let's start with hydrogen peroxide. Hydrogen peroxide is H2O2. So if we were to draw the structure of H2, remember, hydrogens are always attached to oxygen. They are terminal, which means the middle atoms are always going to be oxygen, and then each hydrogen you can distribute it next to each oxygen. So now the skeletal structure would look something like this. I will connect them all with a single bond, meaning 2 electrons, and this is my skeletal structure. Let's figure out what is the total number of valence electrons. We have total of 2 hydrogen. Each hydrogen has 1 electron, so that would be 2 times 1, plus we have 2 oxygen atoms, and each oxygen carries 6 electrons, so this would be 2 times 6. So total would be 2 plus 12, which is 14 electrons. So we need to distribute 14 electrons now. So let's see how many have we already distributed. We have given 2, 4, 5, 6 electrons already. So if I take 6 electrons off from here, I will be left with 8 more electrons to distribute. So I need to give 8 more electrons around. If I were to give 8 electrons, I do not add any more electrons to hydrogen because each hydrogen has formed one bond and they have 2 electrons, they are happy. These 8 electrons are going to go to oxygen, so we start with 1, this would get 2, 2, 4, 5, 6, 7, 8. Let's confirm if every atom is happy and satisfied. Hydrogen has 2 electrons, yes. This has 2 electrons, yes. This oxygen has 2, 2, 4, 5, 6, 7, 8. So this oxygen is happy. This oxygen is forming these many bonds. So this has 2, 2, 4, 5, 6, 7, 8. So this oxygen is also happy. So this structure is correct. Again, remember, don't give me all these smiley faces. This is me showing you how to make this structure. The final structure, you know, is without all these circles that I've drawn. The final structure would be H, single bond O, single bond O, single bond H, and this has these lone pairs. So that would be a final answer to me. But you can, of course, do this as a rough work for yourself. Let's draw the structure of CH3OH. Whenever you see a structure like this, if a molecular formula is written like this is usually an organic compound, okay? If a molecule looks like this, it consists of carbon, hydrogen, and oxygen. Remember, these hydrogens that are listed are attached to this particular carbon, and rest, everything else is attached separately to the carbon, okay? So what that means, if I'm drawing my carbon here, always carbon here would be a central atom. So I'll draw carbon in the middle. Then this carbon is bonded to 3 hydrogens, so I'll draw 3 hydrogens around it. And then what you see is OH. So carbon will be bonded to the O, and this H that you see next to O will be bonded to oxygen. Okay, so this H would be bonded to this particular oxygen in this form. So now we can draw single bonds in between them, and that is our skeletal structure. Let's see how many electrons. There's one carbon carries 4 electrons, 3 hydrogen, each of them has 1 electron, 1 oxygen which has 6 electrons, and 1 more hydrogen which has 1 more electron. So total would come out to be 6, 7, 8, 9, 10, 14 electrons. Okay, so now again we'll start distributing these 14. How many have we already distributed? This is 2, 3, 4, 5, 6, 7, 8, 9, 10. I have distributed 10, so I'll draw another 4 electrons which will go to none of these hydrogens. So we start with carbon. So 1, 2, 3, 4, and that's it. Hydrogen, happy, hydrogen, happy, hydrogen, happy, hydrogen, happy. Oxygen, happy, it has 2, 2, 4, 5, 6, 7, 8. Carbon has 4 bonds, which means a total of 8 electrons, so carbon, happy. So your final structure would be C, single bond O, single bond H, and then each hydrogen, 3 hydrogen next to carbon, and then oxygen would have 2 lone pairs. So that would be your final structure. Okay, Cn minus, this is an ion. This has a negative charge. So now let's draw the structure for this. Here, who will come in the middle? There's literally no middle. One is carbon, one is nitrogen. That's it. Draw them, join them with a single bond. Now let's see how many valence electrons do we have. We have carbon has 4 valence electrons. Nitrogen has 5 valence electrons. We have 1 of each. And you see this negative charge right here? That means it has 1 more electron which is extra. So for every negative charge, add 1 electron. So total number of valence electrons here is 5 plus 5, 10 electrons. So we need to distribute 10 electrons around this. We have already given it 2 electrons right here. Let me draw this because it looks like a double bond now. So we have already given it 2 electrons right here. Now we can start distributing the other electrons. And where should we start? We'll start with nitrogen. Nitrogen is more electronegative, or the definition of electronegativity will come in another video. So for now, just remember nitrogen is more electronegative. So we'll start distributing electrons from to nitrogen first. So how many electrons do we need? total of 10. This is 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have given this total of 10 electrons. Now let's see how many electrons does each of these atoms have. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So this nitrogen is happy. How about carbon? Carbon only has 2, 3, 4. Not happy at all. Very, very unhappy, right? Which means what would happen? This carbon only has 2, 3, 4 electron. It needs 4 more. Where would those come from? This nitrogen will donate, or not donate, but share 4 more electrons. So it will share this lone pair, that would make 1 bond. This lone pair, that would make a third bond. So basically this would consist of carbon triple bonded to nitrogen. This nitrogen will have 1 lone pair, this carbon will have 1 lone pair. And since there is a negative charge, remember this negative charge, do not forget that. Whenever the molecule or the ion that you're working with, if it's an ion, if it has charge, you put your Lewis structure in parentheses and you put the charge up as a superscript. So this is -1, so I'll put a negative next to the structure. This would be your final answer right here. So this bond that we see right here, 1, 2, 3, if it's 3 bonds present between 2 atoms, this is called a triple bond. If there is 2 bonds present between an atom, it is called a double bond. And if it's only 1 bond present, it's called a single bond. Right? So these are some of the examples. Here are a couple more examples. Let's quickly go through those. We have CH3, CH2, OH. Again, whenever you see something with carbons, remember all the carbons have to be bonded to each other. So I see 1 carbon, 2 carbon, which means carbon and carbon are going to be in the middle, bonded to each other. This carbon right here has 3 hydrogen bonded to itself. So I'll draw 3 hydrogen next to it. Always draw this. Okay, this carbon has 2 hydrogen next to it. So I'll draw 1 hydrogen, second hydrogen. There we go. I'll draw second hydrogen next to it. Then we have an OH, and who gets the O? This carbon, one of these carbons, the carbon which is next to will get the O, and then this hydrogen will be bonded to this oxygen. Okay, so this hydrogen that you see as an OH, this hydrogen in the OH is not bonded to the carbon, it is bonded to O. Remember that. Okay. All right, now we have our skeletal structure. Let's find the valence electron. 1 carbon has, the total number of carbon here is 1 and 2. So each carbon has 4 electrons. So I need 2 times 4. How many hydrogen? We have 3, 4, 5, 6 hydrogen atoms. So 6 times 1. And we have 1 oxygen, which is 6. So it's a total of 8 plus 6 plus 6, which would give you 12 plus 8. Total electrons will be 20. I need to give it 20 electrons. How many have I already given it? 1, 2, 3, 4. Oh, again, not a double bond. So I've already given it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I've already given it 16 electrons. So I'm only left with 4 electrons. So I'll start distributing 4 electrons. Who gets those? None of the hydrogen will get it. We start with oxygen. Don't start with carbons. Always start with the terminal groups. So oxygen will get 1, 2, 3, 4. That's it. All my electrons are over. Let's see if everybody got enough electrons and if their octet is complete. This hydrogen is happy. 2 electrons. This hydrogen is happy. All the hydrogens are basically happy here because they have 2 electrons each. As long as they have 1 single bond, hydrogens are happy. Okay. Moving on. Let's look for oxygen. Oxygen has in total this 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's happy. Carbon has 4 bonds. As long as carbon has 4 bonds, it's happy. 4 bond means 8 electrons in total. So carbon happy. This carbon also has 8 electrons. So this carbon is also happy. So the Lewis structure is completed. Okay. Moving on, C2H4. How would we draw C2H4? Remember again, if you see carbon and hydrogen, it's an organic molecule. You start with carbons and you draw the carbons together and then distribute the hydrogens evenly. So I'll give 2 hydrogens to each of these carbons. 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, and connect each of these atoms with a single bond. Now we are going to figure out valence electrons. 2 carbon, each has 4 electrons, so 2 times 4. 4 hydrogen, each has 1 electron, so 4 times 1. The total would be 2 times 4, 8 plus 4, which is 12 electrons. Now let's start giving 12 electrons. We have already given 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all single bonds. I've already given 10 electrons, so I'm left only with 2 electrons. Who would get those 2? One of these carbons. Let's see if everybody is happy. Basically, if you're working with carbon, one easy way to figure it out is as long as carbon does not have 4 bonds, it is not going to be happy. Carbon always wants 4 bonds. But we can also confirm it this way. This hydrogen has 2 electrons, happy. 2 electron, happy. 2 electron, happy. 2 electron, happy. This carbon has 1, 2, 3, 4, 5, 6, 7, 8. 8 electron, happy. This carbon only has 3 bonds, so it only has 1, 2, 3, 4, 5, 6 electrons, so this carbon is not happy, which means this lone pair that is present to this carbon is going to be shared between the 2 carbons, and it would turn into a double bond between carbons. So this bond is now called a double bond. And now nobody has any lone pairs, and this will be the final Lewis structure. Let's finally draw this last structure. This would be consisting of 1 carbon. Then there are 2 hydrogens. Who has the 2 hydrogen? If it is attached to the carbon, you are going to attach these hydrogens to the carbon atom. Then there is 1 oxygen. It has no other hydrogen left, so this would be 1 oxygen. Now how many valence electrons? Carbon has 4, hydrogen has 1 each, and we have 2 of those. Oxygen has 6, so total is 12 electrons. So let's start giving this 12 electrons. We already have given 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a total of 12 electrons. Let's confirm if each octet is completed. This has 2, happy. This hydrogen has 2, happy. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8, happy. Carbon though only has 3 bonds, so it has 1, 2, 3, 4, 5, 6 electrons, so not happy. So what would be the final structure? This oxygen has lone pair, which it is going to share with carbon. So we will be left with carbon attached to 2 hydrogens and then attached to 1 oxygen by a double bond, because this electrons would be shared, and oxygen will be left with 2 lone pairs. So this would be the final structure for this particular molecule of formaldehyde. Okay, so that is how we can draw Lewis structure for any molecular compound. Now another important thing here is what you saw is a double bond and a triple bond. A double bond occurs when atoms share 2 pairs of electrons. So if there is 2 pairs of electrons shared between an atom, this is called as double bond. It forms when there are not enough electrons to complete the octet, like we saw. A triple bond occurs when atoms share 3 pairs of electrons. Forms when there are not enough electrons to complete octet. So if in between 2 atoms you see 3 single lines drawn, that means this is an example of a triple bond. Now, there are some exceptions to this octet rule. I've already told you those exceptions, but we can go through it again. Hydrogen only requires 2 electrons. It does not need 8 electrons in total. Boron usually has 6 valence electrons on its central atom, and boron is happy with having only 6 electrons. So for instance, if we are drawing the structure of BCl3, okay, like here you can see the structure of BCl3. We'll draw B, followed by B will be in the middle. Why? Because it is least number of atoms, followed by 3 Cl atoms, so around it. Now connect each of them with a single bond. How many valence electrons? Boron belongs to group number 3, so it has 3 electrons. Each of these, chlorine has a total of 7 electrons, so total would be 3 times 7, which would be 3 plus 21, so total of 24 electrons. So now we will start distributing 24. We have already distributed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Let's see if they are happy with their electrons. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So this chlorine is happy. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So this is happy. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So this is happy. Boron has 1, 2, 3, 4, 5, 6. Ideally, if it was anything else, we would say it is not happy, but boron is an exception. As long as boron has 6 electrons in its outermost valence shell, boron is also happy. So this is an example of an exception. Next exception was non-metals like phosphorus, sulfur, chlorine, bromine, and iodine can form compounds with 10 or 12 valence electrons. So this is also an exception. Sulfur atom has an octet in many compounds, meaning it usually has 8 electrons, but sometimes, for instance in SF6, there are 12 valence electrons on sulfur. So if you draw SF6, it would look something like this. Sulfur is bonded to 6 fluorine atoms. So sulfur actually has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons instead of having 8 electrons. And this is an exception. Sulfur here is still happy with having more than 8 electrons in its outermost shell. Okay, so here are some exceptions that you need to remember. And next we'll continue with I mentioned something about electronegativity before. So what we saw up until now was all about Lewis structure. Now we will continue with some other topics like what is electronegativity, what is polarity in different types of bonds. Okay, so what is electronegativity? Electro means electron, negativity means negative charge. So the electronegativity of an atom is its ability to attract the shared electrons in a bond. How much love does it have towards electrons? That is called its electronegativity. How much can it pull the electrons towards itself? So the trend of electronegativity, you should remember, it increases when we go from left to right in the periodic table, and it also increases or it decreases when we go from top to bottom. So it increases as we go from left to right, it decreases as we go from top to bottom. Here you can see some numbers of electronegativity, the quantified values of electronegativity for some of these atoms in the periodic table. You're not expected to remember these. If the question is given to you, these values will be provided to you. So you can see right here, based on this, you can see that the metals, usually all of these are metals, the metals usually have a low electronegativity. Okay, their electronegativity is between 0. Something 0.5 to 1.5, 1.6. Some of them is around 2, but most of them are around 1 point or less than 1. Whereas non-metals, you can see, have a very high electronegativity. Everything is above 2. So these are very highly electronegativity. That's why you can see it increases as you go from left to right. When you look at this, cesium is the element that has the least electronegativity, and who has the highest? Fluorine has the highest electronegativity, which means that if fluorine is making a bond, let's say if I make a bond between NaF, okay, what would happen in this case? Na would share one electron, fluorine would share one electron. Remember, if you draw the Lewis structure, it would look something like this. So what has happened here? Sodium has one electron, fluorine has this one electron, and they made this covalent bond. Ideally, these two electrons would be shared in between because they are equally shared by both the atoms. Fluorine is sharing one, so and sodium is sharing one. So ideally you would think electrons would be in the middle. But because fluorine is so much electronegative, it usually takes these electrons and pulls it towards, even though they are still shared. Sodium has not lost its electron, but fluorine, because it is so electronegative, it loves to have electrons next to it. So it is going to pull these electrons from the middle towards itself, and that is called the electronegativity. So if an atom has an attraction, it can pull the electrons or attract the shared electrons in a bond towards itself. That is called the ability. That ability of an atom is called its electronegativity. And this difference in electronegativity gives rise to polarity. So the difference in electronegativity of bonding atoms can be used to predict polarity of a bond. Polarity means unequal sharing of electrons result in polarity. If the electrons are shared equally, then the bond is non-polar, but if the electrons are shared unequally, the bond would be polar. What do I mean by that? For instance, let's say if I'm talking about hydrogen gas. Hydrogen consists of H2. If you draw the Lewis structure, this would be the Lewis structure of hydrogen, meaning one electron is shared by each of these hydrogen atoms. So ideally the electrons should be in the middle. Now think of this as two people, two exactly same people. You can say two identical twins are playing the tug of war. So this hydrogen is pulling these electrons towards itself. This hydrogen is pulling the electron or the rope towards itself. What is happening? They both are identical. They both have the same strength, meaning the electrons are going to stay in the middle. So therefore, if there is no difference in electronegativity, the bond is called non-polar. The electrons are shared in the middle, therefore the bond is non-polar. Whereas, let's say if I'm talking about HCl, if you draw the Lewis structure of HCl, it would look something like this. So now here what is happening? Both the electrons should be shared equally by hydrogen and chlorine, right? Ideally. But chlorine, if you look at the electronegativity chart in the previous slide, chlorine is very highly electronegative in comparison to hydrogen. So what does it do? It gets greedy and it essentially pulls these electrons towards itself like this. So now even though the electrons are still shared, this chlorine has pulled these electrons towards itself. And because of this, this hydrogen gets a partial positive charge, because ideally the electron should be right here in the middle, but these electrons have been pulled away from hydrogen. So it gets a partial positive charge and this chlorine gets a partial negative charge. The symbol that you're seeing me draw, this symbol, is called partial. Partial means it is not exactly a positive charge, so this is not a cation, but it carries a little bit positive charge. And similarly, this chlorine also carries a little bit negative charge because the electrons that should have been shared equally between hydrogen and chlorine are no longer equally shared. Chlorine has gotten a little greedy. It has pulled those electrons towards itself. So whenever you see these charges being formed, this means the bond is polar. So now this molecule is called a polar molecule, and this bond has polarity because the electrons are not being shared equally. Okay, so the bond is polar. The difference in electronegativity values of two atoms can be used to predict the type of chemical bond. The chemical bond can either be polar or non-polar, and we can tell that based on the value of electronegativity difference. So if the electronegativity difference, so what this means is if you have two different atoms, you would look at the periodic table, and let's say if I'm working with HCl again, the electronegativity of H is 2.1. The electronegativity of chlorine from the chart is 3.0. Okay, so what would be the electronegativity difference for these atoms? It would be 3.0 minus 2.1, which is 0.9. Okay, so this is electronegativity difference, meaning you subtract. Difference means you subtract the electronegativity values of the two atoms that are involved in the bond. If this electronegativity difference is between 0 and 0.4, the bond is non-polar. If the electronegativity difference is between 0.4 and 1.8, the bond is polar covalent. If this electronegativity difference is between 1.8 and 3.3, the bond is called ionic bond. And the electrons are considered, ionic bond means the electrons are not shared, the electrons have been transferred. So that is how you can differentiate between three types of bond. One is non-polar covalent, another one is polar covalent. Covalent means electrons are shared, non-polar means electrons are shared equally, polar covalent means electrons are shared unequally. Ionic means electrons are not shared, electrons have been transferred. And the values that it lies within is this: 0 to 0.4, 0.4 to 1.8, 1.8 through 3.3. So basically if I talk about HCl, the value is 0.9, which lies right here between 0.4 and 1.8. That's why this is called a polar covalent bond. So you can differentiate between three bonds by looking at these values of electronegativity difference. So let's say if this is given to you again, all the values that you need, you can get it from the periodic table. You do not have to memorize these values, they will be provided to you in periodic table. Use the electronegativity difference to identify the type of bond. Is it non-polar covalent? Is it polar covalent? Is it ionic? Between the following. So again, you will use the chart to do this. Okay. So if I'm looking at my chart from the previous slide, you can pull that up right now, calculate the difference, okay, and then figure out what is your value. So let's say if I'm doing potassium and nitrogen, I'll show you one of them and then you can do the rest by yourself. So if I'm working with potassium and nitrogen, nitrogen has an electronegativity of 3.0, potassium is 0.8. So what would be the difference? It would be 3.0 minus 0.8, meaning this would be 2.8. Oh, sorry, 2.2. 2.2 meaning this value lies between the value of 1.8 to 3.3, meaning this is ionic in nature. And you can already know this is ionic because this is metal, this is non-metal. Okay, so this bond will be ionic in nature. Another example you can see is right here, Cl and Cl. So the electronegativity of Cl is 3 and 3. So whenever you take difference, that would always come out to be 0, which means this is a non-polar covalent bond. Okay, so you should be able to figure this out. You don't really have to calculate. Whenever it's two same atoms bonded together, it will always come out to be 0. Okay, I'll just give you the answer for these, but you can try them out by yourself. The electronegativity difference, if you calculate for NO, will come out to be 0.5, and the bond will be regarded as polar covalent. So you can try all these questions. The answers are given to you in the slide. Right here, you can check your answers once you have completed solving them by yourself. Okay, this will bring me to the next topic in this presentation or in this chapter, which is called the VSEPR theory. What is VSEPR theory? VSEPR theory stands for valence shell electron pair repulsion theory. Okay, this is based on Lewis structure. Basically, if we can able to draw the Lewis structure, we can predict what is the shape of most of the molecules, and that shape is given by this particular theory, which is valence shell electron pair repulsion theory. What does this theory suggest? This theory suggests that whenever there are valence shell electrons present in pairs, those electrons try to repel each other. Remember, like charges like to repel each other. So when there are two electron pairs next to each other, they will try to achieve an orientation such that these pair of electrons are basically very farther apart from each other as much as is possible to keep the molecular structure intact. Okay, so this VSEPR theory describes the orientation of electron groups around the central atom. It states that electron groups are arranged as far apart as possible around the central atom. So it states that the specific shape of a molecule is determined by the number of atoms attached to the central atom. Okay, so however many electron groups are attached to central atom, they will try to be farthest apart from each other, so that because they are repelling each other, they do not like to be close to each other. Now in here you saw the word electron group. What is electron group? The electron pairs around the central atom are referred to as electron group. Each electron group can be one lone pair. A lone pair basically means two electrons, that is electron group. A single bond is an electron group because each single bond is two electrons. A double bond is an electron group. A double bond is 4 electrons. A triple bond is also regarded as electron group. A triple bond means total of 6 electrons that are shared. So each of these is regarded as one electron group. So how many electron groups are present around the central atom? That would determine what would be the shape or orientation of the molecule. Okay, now this is something that you will have to memorize. What is the shape depending on how many electron groups are present. So for instance, now when we are talking about shape of the atom, we are looking at how many electron groups are present around the central atom. So let's say in first scenario, if the central atom has 2 electron groups around it, what does that mean? These electron groups can be anything: lone pairs, bonds, one bond, one single bond, a double bond, a triple bond. Everything is regarded as one electron group. As long as the central atom has 2 electron groups around it, it would consist of a linear shape. Okay, these electron groups, remember these electron groups, as of now we will first electron groups that we'll talk about will all be bonds rather than lone pairs. Right now we are only talking about bonds. So for instance, if you look at CO2, if you draw the Lewis structure of CO2, you will come up with this Lewis structure where carbon has double bonded to oxygen. So how many electron group does it have? This has, the central atom has 1 electron group. Remember, a double bond is regarded as 1 electron group. And second electron group. So carbon has 2 electron groups, no lone pairs, which means it has a linear geometry. It would look like a linear shape. The bond angle means the bond between two, and the angle between two bonds is going to be 180 degrees, because these electrons that are present, these two groups that are present, they are going to be the farthest apart from each other when they form a straight line. Okay, this is called a linear shape of the molecule or linear geometry. The right structure would be, I think I'm missing an example right here, is H2CO. If you were to draw the structure of H2CO, the Lewis structure, it would consist of C, O, hydrogen, hydrogen. Okay, and let's draw the Lewis structure. How many total electrons does this consist of? Hydrogen has 2, so 2 hydrogen meaning 2 times 1, so 2. Carbon has 4, oxygen has 6, so total is 6, 10, 12 electrons, right? Let's distribute 12 electron. We have already given 2 right here, sorry, 2, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons. But carbon here is not happy. You can see carbon has 3 bonds. So these 2 electrons will be given to carbon, which means our final Lewis structure would look something like this. Double bond O, and O will have 2 lone pairs. Okay, so this would be our final structure. So now how many electron groups are present around this molecule? The central atom, carbon has, this is the 1 electron group, this is the 2nd electron group, and these two this one double bond, remember even if it's a double bond it is regarded as 1 electron group, and no lone pairs. If it has 3 electron groups and all of those are the bonds and no lone pair, the structure is trigonal planar. How would the structure look like? It would basically look like this. Carbon would be in the middle, double bond oxygen. Trigonal means they will take the shape of a triangle. Planar means they will be on one plane. So basically the molecule would look something like this. And the central atom would be in the middle. They will be on a single plane. What would be the bond angle? The bond angle is going to be 120. So this is the bond angle. This is 120 degrees. Okay. Now remember, this is only possible when all of these are all the electron groups are bond. There are no lone pair. But there is also a 3 electron groups. Okay, so it has 3 electron groups, out of which one of them is a lone pair. So for instance, SO2, if you draw the structure of SO2, it consists of the central atom has one bond, then a double bond meaning a 2nd electron group, and a lone pair. So if it has 3 electron groups, and if one of those is a lone pair, the structure is no longer trigonal planar. The structure is called bent. The angle is still 120 degrees, but the structure is now bent instead of trigonal planar. So this happens when it is 3 electron groups and at least one of those is a lone pair. Whenever there is one lone pair present, the structure becomes a little bit different. Okay? Most of the times it is called a bent structure. Moving on. What happens if the central atom has 4 electron groups? If it has 4 electron groups and all of those are bonds, the shape is called tetrahedral. For instance, the first structure we draw was methane, CH4. This is called a tetrahedral geometry, and the angle that is present, bond angle, is 109 degrees. This is called a tetrahedral geometry. Again, this is only possible when it has 4 electron groups and all of those 4 are bonds. There are no lone pairs. Okay. What happens if there are 4 electron groups and one of them is a lone pair? So for instance, ammonia, NH3. If you draw the structure, it would come out to be this. It has 1 bond, 2 bond, 3 bond, and a lone pair. So nitrogen here, central atom, has 4 electron groups with one of them being lone pair. So in this case, the shape would be called trigonal pyramidal. Okay. And the bond angle would still be the same, it's 109, but the shape is no longer tetrahedral, it is trigonal pyramidal. Okay, as long as there's one lone pair, the structure would be different. Right? Okay, more if there are 2 lone pairs. Okay, for instance, in case of water, if you draw the Lewis structure of water molecule, the central atom, which is oxygen, consists of a lone pair, 1 electron group, 2 electron group, 3 electron group, and 4 electron group. Total is 4, out of which there are 2 lone pair. If there are 2 lone pair, the structure is also again called a bent structure. Here, this is called the tetrahedral bent. Okay, so I would put here tetrahedral bent. Tetrahedral bent again carries an angle of 109. So this is also a bent shape, just like we saw previously, right? This is only when it has two lone pairs. So this is something that you would have to memorize for yourself, which uh, type of electron group will result in what shape. So basically a summary of everything. If it is two, this is the easiest way to memorize it. If it is two electron groups and there are both of those are bonds and lone pair is 0, it would be linear shape. The bond angle is 180. If it is three groups, there are two possibilities. If it is three where three of them is bonds, no lone pair, it is called trigonal planar. Angle is 120. If it is three electron groups, but there is one of those is a lone pair, it would be a bent trigonal shape, 120 degrees. This is not a planar structure anymore, it is a bent shape. Next we see four electron groups. It can have three different shapes. If it is four electron groups and it is only all of them are bond, there are no lone pairs, it is tetrahedral. If it is one of those is a lone pair and only three are bond, it is trigonal pyramidal. If out of those four, two are lone pairs and two are bonded two are bonds, it would be bent shape. So this is basically summary of all the shapes that can be present and how you can predict what is the shape of the molecule. Okay. Oops, let's draw this again. So I have sulfur, hydrogen and two electrons, right? Total number of valence electrons here was, hydrogen was 2 electrons, so 2 times 1. Sulfur was 6 electrons, so total is 8 electrons. So this would be our Lewis structure. Now if I were to go and decide what would be the shape, it has, the central atom is sulfur, it has 4 electron groups, right? Out of these 4, 2 of them are bonds and 2 of them are lone pairs. So now if you go back and look at your chart of the structure, you would say this would compose a shape which is tetrahedral bent shape. So this would be tetrahedral bent. The angle would be 109 degrees. So you can use the same approach to figure out what would be the number of electron groups, lone pairs, and the shape of any molecule. Okay, so you guys can practice these questions on yourself, by yourself, and let me know if you come up with any issues. Okay. Moving on, we talked about polarity of the molecules. So right now what we talked previously was if a bond is polar or not. Okay, now we will talk about if a molecule is polar or not. So what decides if a molecule is polar or not? First we have to figure out if the bonds are polar in a molecule. If the bonds are polar, the polarity of the molecule will depend on its geometry. Okay. For instance, why the molecules like hydrogen, chlorine, oxygen are non-polar? Why? Because they contain non-polar bonds. We saw that. Because for instance, chlorine will consist of Cl. The electronegativity of this chlorine is 3, this chlorine is 3. So the total difference comes out to be 3.0 minus 3.0, which is 0. Therefore, this bond is non-polar. But sometimes, even if when the bonds are polar, the molecule can be non-polar. How? If the polar bonds cancel in a symmetrical arrangement. For instance, if we talk about CO2, in case of CO2, oxygen is more electronegative than carbon. So what happens? Imagine this is polarity. So polarity means this oxygen is pulling the electrons towards itself. This oxygen is pulling the electron towards itself. Oxygen here, both oxygen are pulling the electrons away from carbon at the same strength, right? Again, it's a tug of war. So what would happen? The polarity that is generated by this and polarity that is generated by this will cancel each other out. the polarity in a bond is also referred to as dipole. So dipole here always goes, the direction of dipole goes from partially positive to partially negative, to the more, from less electronegative to high electronegative compound or atom. So here the polarity, direction of polarity is basically going from carbon to oxygen, carbon to oxygen. So they are both pulling them in opposite direction. What would happen? They will cancel each other out. So the molecule will be non-polar. Similarly, if we talk about a molecule like CF4 or CCl4, like shown here, here the carbon is bonded to 4 chlorine atoms, okay, in this form. So the shape is tetrahedral. This is the tetrahedral shape. All these 4 are basically pulling carbon in towards themselves. What would happen? These 2 will pull, these 3 will pull it together and will become equal to the final. If you think about it, the carbon is basically being pulled downward, and this chlorine is pulling the carbon upward. So basically they will cancel, all these polarities or dipoles will cancel each other out. The molecule will be non-polar. Okay, so non-polarity of a molecule would finally depend on the geometry of the molecule. Moving on, polar molecules such as HCl are polar because here one end of the molecule is more negatively charged, more electronegative than the other. Here, the secondly, the polar bond that is present in the molecule, there's only one polar bond. There's no cancelling here. Nobody is cancelling each other's polarity. And then the electrons are shared unequally. Therefore, this bond is polar. And therefore, this is a polar molecule. In polar molecules, what happens essentially, for instance, right here, when we talk about water molecule, if you draw the Lewis structure, it would look something like this. So what happens here? Oxygen is very electronegative, so it basically pulls the electrons towards itself. Hydrogen is the poorest of the poor on the periodic table. First thing, it has only one electron, and then it has so less polarity that other atoms basically pull the electrons away from hydrogen. So hydrogen here would become partial positive and oxygen here would become partial negative. Okay, so which direction would be the polarity? The overall polarity, you can think, is going towards oxygen. So if you sum these up, the average polarity of the molecule will be basically towards oxygen. So this is the dipole direction. Dipole will be basically going from hydrogen to oxygen. So therefore water is regarded as a polar molecules because these polarities do not cancel each other out. Instead, they will be added together because they are both going in the same direction. So again, tug of war, you can imagine this oxygen is basically pulling this hydrogen and this hydrogen. So since hydrogens are very weak, they will be pulled, both will be pulled towards upward direction. Another molecule example you can see is ammonia. What would happen in case of ammonia? If you draw the structure, here also nitrogen has one lone pair. These nitrogen is again more polar than hydrogen, so they will also be pulling in one direction. The shape of this molecule is going to be trigonal pyramidal, which means they will be all in 3 different directions. So nitrogen, one would be hydrogen, second hydrogen, third hydrogen. They are in 3 different angles at an angle of 120 degrees. So if that is the case, this hydrogen is being pulled up, this is being pulled up, this is being pulled up. So overall polarity would be towards nitrogen. Again, the polarities would be summed up instead of being cancelled. Therefore, the molecule would be polar. Okay. So if some question is asked, can you determine the polarity of the molecule? First thing you have to do is determine if the bonds are polar or non-polar. If the bonds are polar, in that case you would draw the Lewis structure, determine the shape of the molecule, and then see if the dipoles are cancelling each other out. If they are not being cancelled, that means that the bond is basically a polar bond. If they are being cancelled, that means the bond is non-polar. Okay, so we can try here. here. For instance, if we are working with PBr 3, what would happen in this case? First thing, you are going to look at the chart that was shown before to you. Phosphorus has electronegativity of 2.1, Br has electronegativity of 2.8. So what each bond, again you don't have to worry about how many bromine are present. Each bond between phosphorus and bromine, okay, each bond here we have to see what would be the polarity or what would be the electronegativity difference. It would be 2.8 minus 2.1, which would give you 0.7. 0.7 basically means that the bond is polar. Now, because the bond is polar, we have to see what would be the Lewis structure and shape of this. So first let's draw the Lewis structure, which would be phosphorus here, Br, Br and Br, all by single bonds. Each phosphorus has how many electrons? 5. We have 3 Br and each Br has 7. So total would be 5 plus 21, which is total of 26 electrons. So let's divide 26 electrons here. We already have 2, 2, 4. Oops. So 2 electrons are here, 2, 4. Oh my god. Don't want to make it into a double bond. So we have 2, 2, 4, 5, 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So what would be the shape of this molecule? This phosphorus has 4 electron groups, out of which 1 is a lone pair. When it is 4 electron groups and 1 is a lone pair, the shape basically becomes a trigonal pyramidal, right? So how would we draw trigonal pyramidal? It would basically look like this. So phosphorus would have 1 lone pair, and then we would have 3 Br right here, and each of them would have lone pairs next to them. So in this shape, what would happen? Again, who is more electronegative here? The bromine atom is more electronegative, which means these would be pulling it towards itself. You can see right here, bromine is more electronegative, so the dipoles would be towards bromine, and each of them is being pulled towards one direction, which means the polarity would lie in this direction in total. So they are not cancelling each other out, so the molecule is polar. Okay. Similarly, you will try the other molecule like HBr. HBr is fairly simple. Hydrogen is 2.1, bromine is 2.8. So the bond again is 0.7 difference, which means bond is polar. If I draw the structure of HBr, Lewis structure, it would look something like this. This bond, you can see definitely the polarity is towards bromine, which means the bond is polar. There's no cancellation happening here. How about CH4? Carbon is, for carbon electronegativity is 2.5. For hydrogen it is 2.1. So what would be the difference? 2.5 minus 2.1 will give you 0.4. Remember, 0.4 means the bond is non-polar. If the bond is non-polar, if you draw the structure of CH4, the Lewis structure would, the Lewis structure would look something like this, which means the shape of this molecule is going to be tetrahedral. And since each of the bond, you don't even have to go here because each of the bond is non-polar, the molecule will be non-polar. You don't even have to draw its Lewis structure, come up with the shape, because if the bond is non-polar, the molecule is non-polar. So that is how you can predict the polarity of a molecule, right? And I think that would be the last thing that we discuss in this particular section of this chapter. The answers are also provided to you in the slide.